This is Module 8. We're going through Example 1. We're going to discuss and try to get an understanding of the effect on the sampling distribution when we change the sample size. Let's read through the problem. So suppose we're interested in understanding a population parameter pi. We hypothesize that the true value of pi is 35%. So the null hypothesis is that pi is 0.35. I collect a sample. My sample statistic is p hat equals 18 out of 40, so 45% success. My friend Bob also collects a sample, and Bob gets a sample statistic of p hat equals 90 out of 200, which is also 45%. Now I'm just going to stop for a second here in my reading and kind of look at that. Notice Bob and I both have a p hat equal to 45%. So in some ways we have the same sample statistic. However, notice my sample statistic was 18 out of 40, so I had a sample size of 40. And Bob had a sample statistic of 90 out of 200, so Bob had a sample size of 200. We got the same sample statistic, 45%, but we had very different sample sizes. Bob had a much bigger sample. I want to look at the actual distribution of sample statistics, the null distribution, and see the difference between Bob's null distribution and my null distribution, and really try to get an understanding of the effect of that sample size, the effect that it has on the null distribution, and ultimately then the effect it will have on our conclusion about the null hypothesis. So we're going to come down here, we're going to label my null distribution and Bob's and make conclusions for each. Okay, so let's start with mine. So my sample size, remember, was a sample size of 40, and it says, question, what is the standard deviation of this distribution of p hats? This is the null distribution, the distribution of sample statistics, the distribution of p hats. We know from the central limit theorem that it is bell-shaped. We know from the central limit theorem that it will be centered at the value of the parameter from the null hypothesis, which is pi equals 0.35. And we also learned that the standard deviation of this null distribution is given by the formula square root of pi times 1 minus pi over n. That's called the standard error. Okay, so there's the standard error formula. To find the actual standard error, we're going to take that formula and we're going to plug in the values that we know from this particular problem. So in this case, pi is 0.35. We're hypothesizing in the null hypothesis that the true population parameter is 35%. So I'm replacing pi with 0.35. And we're talking about my sample. My sample had a sample size of 40. I'm going to pop that in my calculator. Again, remember, you can use Desmos.com as a good calculator. In Desmos.com, I go to Scientific Calculator. I hit the square root button, and then I hit the fraction button. In the numerator of the fraction, I have 0.35 parentheses 1 minus 0.35. In the denominator, I have 40. And I press enter. So I get a standard error of about 0.08. So my answer here for the standard error is 0.08. Okay, so that means that the distance between each of these vertical lines is 0.08. The standard deviation of the null distribution is 0.08. So now I've labeled the horizontal axis with the values that correspond with a standardized statistic of 0, 1, 2, and a standardized statistic also of -1 and -2, which is all those vertical blue lines. Okay, then over here on the right, we have another question posed. It says, is my statistic, which was p hat equals 0.45, an unusual statistic in this distribution? I see that my statistic of 0.45 would land here between a standardized statistic of z equals 1 and a standardized statistic of z equals 2. It's here between 0.42 and 0.5. It'd be about here. So the z-score of my statistic will be somewhere between z equals 1 and z equals 2. And that's not unusual. Remember, we would think of something as being unusual if it was more than 2 standard deviations away from the middle. I could actually now even find the standardized statistic. I could find the z-score. The z-score for this statistic would be 0.45 minus 0.35 divided by 0.08. Remember, statistic minus the mean of the null divided by the standard deviation of the null distribution. If you pop that in your calculator, you'll get 1.25. So my statistic is 1.25 standard deviations above the mean of the null distribution. So it's not unusual. Since my statistic is usual, normal, and expected in this null distribution, I conclude that the null hypothesis is plausible. It's plausible that the true population parameter is 0.35. Okay, so I had a sample size of 40. My statistic was about here. 0.45 was about here. 1.25 standard deviations above the mean of the null. And that turns out then that we'd say the null hypothesis is plausible. Now remember, my friend Bob also did a sample, but Bob did a bigger sample. Bob's sample size was 200. This is Bob's null distribution. Notice it's still bell-shaped. It's still centered at the null hypothesis value, which is 0.35. And it says here what is the standard error of the null distribution. What is the standard deviation of this distribution of sample statistics? So again, we're going to use the same formula, square root of pi times 1 minus pi over n. And again, I plug the values in. Pi is still 0.35, but the value of n in the denominator is now 200. Notice, since I'm going to be dividing by 200 instead of dividing by 40, it's going to make this whole thing much smaller than it did in the first problem. So I'm going to pull out Desmos. Okay, and I've typed it all in Desmos here, and it says that the standard error is 0.03. Notice that is smaller than it was for the first sample. The first sample had a standard error of 0.08, so the distance between the vertical lines was 0.08. Now, with a bigger sample size, the distance between the vertical lines is only 0.03. When I go through now and I label, all right, there we go. So 0.35 in the middle. You add 0.03 to get 0.38, add another 0.03 to get 0.41. Going backwards, you subtract 0.03 to get 0.32 and subtract 0.03 to get 0.29. So notice there's a much smaller range of what we expect to get for sample statistics. The distribution of sample statistics is much narrower than it was when we did the sample with sample size 40. Let's just compare those directly here. So notice above, when the sample size was 40, this distribution was more wide, it was more spread out. And now with a sample size of 200, it's thinner. They both still have the bell-shaped. They're both still centered at 0.35. But when your sample size increased to 200, that made the standard deviation of the null distribution smaller. So it made all of this happen on a narrower range of values. Now, 2 standard deviations below is down to 0.29. 2 standard deviations above is up to 0.41. Whereas up here with a sample size of 40, we went all the way down to 0.19 and all the way up to 0.5 to get that normal, usual, expected range of values, 2 standard deviations. Okay, finally then it says, what about Bob's statistic of 0.45 on this new distribution? Is it usual or is it unusual? Now notice 0.45 is up here now. 0.45 is beyond 2 standard deviations. 0.45 is in the realm of unusual sample statistics. It's going to have a z-score that is bigger than 2. Okay, so I say this time that the statistic is unusual because it's more than 2 standard deviations above the mean of the null. That happened because when we increased the sample size, it made the distribution of sample statistics narrower. So to find the actual standardized statistic, we can find the z-score. The z-score this time is our statistic, 0.45, minus our mean of our null, which is 0.35, divided by the standard deviation of the null distribution, which is 0.03. We divide that out, we get 3.3. Bob's sample statistic is 3.3 standard deviations above the mean of the null distribution. So, since Bob has an unusual statistic, Bob would conclude that he has very strong evidence against the null hypothesis, and Bob has strong evidence that it is not 0.35 since his sample statistic is so unusually high.